we'll get going here. So, all right, so pull open those two sections of code. I want today to mathematically, I don't know what that means. Mathematically, okay. I want to just do a quick review of last time. So hopefully you've had a chance to watch that quick screencast. I'm sorry that I wasn't able to be here. I had some major internet issues. And so if you've got a chance to watch the screencast, then this will be old news. But if you just run the incremental search example starter code, we're going to end up with a plot, which is what we looked at last time. And so this is a plot using the sub function that's embedded in this script of sine 10x plus cosine 3x. And so, and what we talked about is just using the zoom features really simply. We can zoom in, to these intervals, and if you zoom in enough, then we can get that our root is between 4.23 and 4.23. So this gives us 2 decimal places of precision in our root. So we're zooming in, zooming out, and using a graphical method to identify these roots. The next thing that we talked about doing was identifying the roots using the f0 function. Okay, so root number 1, for example, would be f0, and then using the @ command, which is calling the function handle. The function that we are using here is test function. And then we can either give it 1 input or 2 inputs. And so if we go back to our plot, and we know we want to get this root, which we're saying is 4.23. If we zoom in enough, then 4.229 is the answer that we're looking for. And if we then put in a single guess, 4.228, for example, let's see what it gives us for our root. It actually gives us 3.75. We worked through that example. It's actually picking a root from over here. So we need to give it a better number. 4.229 is the answer we're after. So let's go 4.23 and run it. And it gives us 4.23. Oh, it looks like I've got my format. I need to change this back to short G. There we go, 4.229. Okay, so this was the basics of last lecture. But there was one more option here that we could use for using the f0 function, which is this time-tested function from decades ago. And that's using a bracketed number or a one-dimensional array. And so from that, excuse me, we could use 4.2 to 4.24, and then when we run this, we will also get the same root that we're after. And what we've done there is we've said, all right, I'm going to put, forgive me for the screaming in the background, but we're going to put in a number to the left of our root and then a number to the right of our root. And so what we're doing here is we're bracketing the root. And so today we're going to talk about the mechanics of how to come up with the bracket. Okay, like where would I get 4.2 and 4.24 without just a visual inspection, but can we use MATLAB to come up with that bracket itself? Okay, does that make sense? Give me a thumbs up if you're following me. Okay, got a few. Okay, and so the whole point here is that I think I need to go handle this. Excuse me, guys. So, all right, so let's get back to this. So the question here is, when we're using f0, okay, there are a couple things that are happening inside there, and we're going to start decomposing it. So the first is that where in the world would we even come up with our brackets to then put into f0 is what we're at. And so it would be just a pain to take this function and have to say, I need to come up with 2 numbers here, 2 here, 2 here, 2 here, and all these brackets as we're moving through graphically to then put it into the function. okay? So that's what we're doing today. And so, guys, sorry about this. Okay, so now what we need to figure out now is how to start to figure out these brackets. So instead of looking at this graphically, what is the way that we can work through incrementally, okay, and that's really the word that we need to be thinking here, incrementally within this function, and find out where a 0 exists and where it doesn't. So that's ultimately what we're after, to then come up with these brackets, okay? So we're inserting this interval, and so what is, and there's just a question for you, is what is the mathematical way that we could come up with that if I say between 4.2 and 4.224, okay, so this is now over here, between 4.20 and 4.24, how would you determine that there is a 0 there or not? Does my question make sense? So we're looking here between 4.2, 4.24, that's my bracket. But then how do you determine whether there's a 0 or not? So give me a mathematical way of figuring or of answering that question.
Just be wherever the function is 0. So I guess, I mean, I don't know if that's what you're looking for, but can't you just somehow compare, like somehow plug the values in or whatever between those points and then see if it's equal to 0, then you know blank.
Okay.
No.
So let's see if it's 0. So so can you, well, here's another question for you. Like if we're looking at this plot, is there necessarily a point that's on 0?
Hold on, I'm sorry, I might be thinking of something else. So
yes,
you find.
So my question is, on this plot, is there necessarily a point that's on the 0? So let me, let's go back to our code. And so here, let's do some circles, okay? And let's take our increments back down to 100. Let's take it out of 1,000. So I'm gonna run it, all right? Oh, let's try 1,000. Right. I'm gonna zoom in again. And so kind of what Carter's saying is like, okay, I just want to give me the point that's on 0. All right, and so now it kind of raises the question, is there a point that's on 0? Like, can we do a test and say, is there a y value that's on 0? And we've put 1,000 data points in there. So the answer is no, but we know that there's a root here. So how would we say on the increment between 4.2 and 4.24, yes, it crosses 0. That's what I'm looking for now.
If you evaluate the numbers on either side, if they have a different sign, like one's negative, one's positive, then you know it crosses the x-axis. It doesn't guarantee there's a point on the line because you could have like a gap in your graph, but it's a pretty good indicator.
Got it. Okay. Yes. So I wanted, that's exactly what I'm looking for. Is I want you to be thinking about signs. Okay. So we know that there's a 0 in this region, right? So there's a root in this region. Left of here, it's positive, and then to the right, it's negative. Okay. And so as a result, we want to know when that sign changes, right? So, and Elliot said we want to evaluate that, okay, at a couple different places. And so come up with the conditional statement, or at least a logical statement. Let's not do a conditional, but what is the logical statement that we can use? And let's say, so we're evaluating test function, right? That's our function. So test function at 4.20, right? And I can evaluate test function at 4.24, okay? And we should see that this is positive and this is negative, okay? So let's just run that. And that's what we get. So we get a positive value of 0.082913, and then our second is negative 0.011712, okay? So now what's my logical statement to say that the sign changed? Like what can you come up with here?
like if the difference is greater than or less than 0, think greater than 0, like
Okay.
the difference. Yeah.
So if the difference is greater than 0, something like this.
Yeah, I think so.
Okay. And so then if it's greater than 0, then what is that going to tell us? Does that mean that there is a sign change or there's not a sign change?
That there isn't a sign change.
That there isn't a sign change. So if we run this and we say,
so it would be, yeah.
So I've got a logical 1 would say that there is not a sign change. But we know there's a sign change here. So instead of a difference, I want you to be thinking of another arithmetic property. Let's multiply them. Okay, so if we multiply them, okay, and we've got a sign change that's going to occur. So if there's a sign change, then what should be the sign of this? Should it be greater than or less than 0?
Be less than if you're multiplying by a negative.
Yeah, so if it's a positive times a negative, which is what we're looking at, this is always going to be less than 0. Okay, so let's run this again, and we should see that we get this statement is now true. We get a logical 1, okay, which is saying this statement is true, and so this is our statement for sign change occurs. Okay, and this would go in the if, like if this occurs, then we've got a sign change. Okay, does that make sense? Give me a thumbs up if you're following me here. Okay. Zach, William, Alexis. Okay. All right. Okay, great. So we need to have some logic in here, and we'll get into how to put in the interval in just a second. Okay, but let's test the next interval, which is 4.24 to 4.30. And so here, this is looking at this next little bit, 4.24 to 4.30, we should see another sign change, correct? Okay, so we're now looking at that second root near this local minimum. So we can do our test function, does the sign change occur? And I'm going to call this sign change 1. I'll call the next one, here's our second word testing, so sign change 2. And so this is 4.24 to, we said 4.3. Okay, and we should get a logical positive. We should get a positive test with this as well. And we do, right? Sign change, sign change. Okay. And so we're saying, all right, we've got a 0 crossing here. There's a root. Okay. But then what happens when we test it for 4.20 to 4.3? Okay. We should see here that in that section, all right, we've actually got 2 roots. And so let's run that. Sign change 3. And we get a logical 0. Okay, so what we're seeing here is that this test for whether there's a root there or not is going to be insufficient if we're using 4.2 and 4.3, because we can graphically see there are 2 roots there, right? But our test, if this is our test for whether there's a root or not, the sign change test fails. Okay, is everybody following me? So what we're essentially testing, so I guess what is our limitation here that we're seeing with the sign change criterion for whether a root exists?
You're not going to be able to see double roots.
Yeah, we're not going to be able to see an even number of roots. So if there's 2, if there's 4, right, we're going to have the same sign, positive, positive, or negative, negative, when we're evaluating that function. So we can only determine that there are roots that exist if there is 1, 3, 5, 7, and so on, an odd number of roots. Okay, if we're looking for a root exists and a root doesn't. Okay, so does that make sense? Now,
could you go over that concept one more time, please?
Yeah, sure can. So we're evaluating the question of whether we can use mathematically. Here was the question: can we mathematically determine if there's a root on an interval? Okay, and so we came up with we're looking for a sign change, and so if that's our test, then we need to see a sign change for a root to be there. And so in looking at these intervals, so 4.20 to 4.24, there should be a sign change between this point and this point. Okay, so we pass, there's a root right here. Or if we go from this, 4.24 to 4.23, there is a root in between it. But if we apply that test to 4.2 to 4.3, then we get that the test doesn't pass. We get a logical 0, which means that no sign change occurs. Okay, and if we're using sign change as our interpreter as to whether a root exists, we've actually just failed that test. And it's because there are two roots. It crosses 0 once and crosses 0 again. So we have a positive value and a positive value, no sign change. And so it ends up failing the test when looking at two roots. And I made the comment that that's going to be the case anytime that we're looking at an even number of roots or an odd number, an even number of roots. Okay, so for example, if here's my increment, and I've got an increment, let's say from 3.6 to 4.9. Okay, there's an even number of roots. There's 1 root, 2 root, 3 root, 4 root. So let's type in 3.6 and 4.9. This will be sign change 3. Okay. And then we see I get a logical 0, and it's telling me there are no roots between 3.6 and 4.9. But we know that's not the case, right? We know there's actually 4 roots there. Okay, but if I did, if I applied this test between 3.6 and 4.5, then this test of whether there are roots or not, it's going to say, yes, there are roots. Did that answer your question, Federico?
Yes, thanks.
Okay. And you can come back and watch this again. But the concept here is that this test itself only works for an odd number of zeros, odd number of roots, and not an even number. Okay. And so how do we fix that? How do we make it so that this test is going to work? We make sure that our increments are small. Okay. And you have to excuse me one more time. I have an aspiring 3-year-old pianist. And so our goal here now is to be able to identify roots on an increment, okay? And then this incremental search, the idea is to actually take an increment, okay? And then that's small enough and move it from left to right through the function, and then answer the question over and over and over, does a root exist? Okay, and that's the incremental search. And from that, if a root exists, this is a positive, negative, or we're saying, just give me that increment. And if a root exists, then we can apply the F0, and it'll go get that root. And then that takes away our need to zoom in and come up with, what increments that we need left and right of every single root here. Okay, we're trying to take that work away by doing this. And so, so what I want to do is let's come up with some pseudocode to make that happen. And so again, we're going to be walking our way through increment by increment by increment. to find out whether a zero exists or not. Oh, and one more comment. We just now did a brute force multiplication test, okay, for a sign change that occurs, and you can run into a round off error issue here, in that if you multiply a really small number by a really small number, okay, what are you going to get? Like if you got something close to zero, then multiply something close to zero, then you're going to get what? I can't hear you. Are there people talking?
Something even smaller.
Something even smaller, right? So you're going to get something even closer to zero. And so one problem that we run into is that your computer can only handle so many decimal places, so many digits. And so, it's possible that we run into an error by multiplying a small number times a small number, super small number times a super small number, and getting past the ability of the computer to represent the number that's so small. Okay. And so to get around that, instead of using the multiplication function like we have here, type in help sign. This is the signum function. And then this, the way that this is organized, it's, for the way that this is organized, it takes care of that type of error. Okay. And the name of that error is called underflow. Okay, when you can't represent a number close to zero, okay, that's called underflow. When you can't represent a large number, it's called overflow. Okay, so it's called an underflow error. And so instead of using the multiplication, like what we did now, when using that test, actually use the sign of x. Okay. Now, and you'll be able to get that sign change and make that comparison. So sign of this compared to sign of this is going to be equal to each other or not. Okay, so that's actually the test you want to use. So let's glance at what that pseudocode would look like, or come up with what the pseudocode would be. And so so here for an incremental search function, and this is in the incremental search function, so don't peek at that. But if we're looking for the pseudocode for an incremental search, then what is it that we would have to do? We would first need to come up with our intervals, right? So if we're gonna be looking for this entire, we want to place lots of intervals throughout this code, we need to come up with our intervals. So we're going to define the intervals, okay, across the domain of the function. Okay, and then we need to define the intervals, okay, where they begin and where they end, but we also need to calculate the value of the function at each of the edges of the interval. Okay. And that's what we were doing just a moment ago, is we were just taking a single interval, and if 4.20 is the edge of the interval to 4.24 being the edge of the interval, okay, we then calculated the function at that bottom edge, or the lower edge of the interval, and then the upper edge, or the upper limit of the interval. And then what did we do after that? We just tested it for a sign change. Okay. So then, as we're looking through this, we want to test the values at each edge for a sign change. Okay. And then this test is going to go in a loop. So we're going to loop through the intervals and detect a sign change from the start and end of the interval. So we're going to do that for each one. And then after you've done all this, and there's a little bit more details that you would put in this, but then after all this is over, we of course want to display what we want to identify. Okay, after we test the values of a sign change, we would say, if a sign change, then we want to pull out the bottom limit and the upper limit of the interval and call that a bracket. Then call lower bound and upper bound a bracket. Okay. And so we're saying within that bracket, a 0 exists. Okay, and that's the whole goal of this. And then of course we want to display all the brackets located in the function on the domain specified. All right, so we give the user, all right, we've got a lower and an upper, lower and an upper, lower and an upper, lower and an upper. Okay. And then the last thing is we started out last time by saying always plot your function. Okay, always plot your function. So plot the brackets on the function as a check or to verify that all roots, or let's say all brackets around roots are found. Okay. All right, so does that sequence, can it kind of follow along with that sequence of getting our brackets? Okay. And so then let's go back to our code. And we have this incremental search starter code. And so what's in this incremental search, okay, the incremental search to locate the intervals or the brackets in which a root definitely exists, because that's what we want, something that definitely exists, and then can be incorporated into a direct search of the root. Okay, so the inputs here are the function handle, just like we used with the F0 function. We need to give it a minimum and a max. Okay, and these are the endpoints of the domain in the X to be searched with the brackets. Okay, and then we've got an input of the number of intervals to use. So if we have between 3 and 6, right, we can then say, all right, split this into so many intervals. Okay, instead of trying to give it the interval, just say split it into so many intervals, and we can decide whether that's enough or not. And then this number of intervals is an optional input. Okay, and so meaning that you can put whatever number you want. Okay, if we do 2 intervals, we say I'm going to search in the left half, 3 to 4.5. Okay, that's going to be, and then the right half, it's only 2 intervals. We know that's going to be too few, right? If we say it's going to be 4 intervals, it's going to be too few. So in this code, the default interval is 50, and so we did. So what you'll see here is that there's a little bit of defensive programming here at the beginning, okay? And it's using a function called inargin. And inargin, let's do a slight digression into this. So inargin is part of a series here of inargout, varargin, inargin check, and so forth. And so inargin is the number of the function input arguments. Okay? So there's potentially 4 arguments: function handle, xmin, xmax, and max and number of intervals. Okay, and the defensive programming here is saying we need to make sure that there is a minimum number that's here. And if your intervals, number of intervals, is your optional input, then that means we need to have greater than 3 arguments. So 3 or more, at least 3 arguments are required. So if inargin is less than 3, then the function isn't ready to go. Like the user hasn't used them correctly. But we can say, all right, if this isn't an optional one, then inargin, if it's less than 4, then we can assume that the user just said, give me as many intervals as we need. Use whatever the default is, it's 50. okay? And we're not putting any smart programming in here to adjust those intervals, but it does need a default. And so when calling this, let's call it and get our brackets. And so let's use the incremental search function. And this starter code, oh, looks like that's misspelled. You're gonna have to fix that R that's there. Sorry about that. So the starter code, we'll give it the function handle. So it's called test function. So we're gonna give it the @ test function. My xmin is 3, my xmax is 6. This is our domain that we're searching in. And then let's just leave off the number of intervals. Okay. And our logic should be correct. If we run this, and at the bottom, well, let's see here, we've left that off. Let's actually talk through the code a little bit. We're defining the edges of the intervals that we talked about for a moment. We've got to come up with a set of intervals to investigate, then going to identify if the root or an odd number of roots exists on the interval by looping through the intervals and determining if a sign change exists. Okay, so here's our loop. So for I, 1 to the number of intervals, and then defining bounds, a lower bound and upper bound of each interval as it loops through. And then here's the logic. If the sign of the function at the iteration, at the edge, at the iteration, so this is our lower bound, and actually I could have put that in by this, just saying the lower bound sign of lower bound is equal to or not equal to the sign of the upper bound. Then if these two signs are different, then we want to store the lower bound and upper bound in the brackets. And so then at the bottom, we're going to display the number of brackets. So the number of brackets found, down here, number of brackets found are equal to so many brackets. And then the displaying the lower bounds and upper bounds. But then also there's a check right here that's saying if the number of brackets is empty, meaning there's nothing there, then we would say no brackets are found. So that's meaning that there are no roots according to this, or there's an even number of roots throughout the whole function. Okay, so we'd have to make some adjustments. And so when we run this, oh, it looks like I may have messed up my code. Bummer. Let's put those back in. All right. So then the brackets that I have, lower bound, upper bound, 3.24 to 3.30. There we go. So 3.24 to 3.30 gets this root, 3.36 to 3.42, 3.72. You can zoom in on these. 3.72 to 3.78 it got. So it seems like it got that. That's nice. These are the ones we talked about earlier, 4.20 to 4.26 gets our root we were exploring. 4.26 to 4.32 gets this next root here. And then we've got 4.68 to 4.74. So that's this guy. And then we're actually running into a problem. Can you see that? Our next root is 5.64 to 5.70, which is over here. And we've missed these two roots. Okay. Like, can everybody see that? So what's our solution to then be able to bracket, put a bracket here, bracket there, bracket here, bracket there, left and right of each of those roots?
Decrease the interval size. So I guess the spacing between each.
Yeah, so we're going to decrease. Yeah, exactly right. So we're going to decrease the interval size. And we're going to do that by increasing the number of intervals in the domain that's being searched. And so that means we'll put in that fourth argument that we've left out. 50 isn't enough. So what do you want to use?
Doesn't matter really, I guess, as long as it's small, correct?
Or as long as it's large. So we want
I'm
to
sorry.
increase the
Yep.
number of enumerables.
Right.
Let's try 100. Okay. Let's see if that gets it. And it looks like it did. So 516 to 519. I'm going to take off those circles since we're not illustrating that point any longer. So 516 to 519. And then 519 to 522. So 5. All right. So 519 to 522. Yes, 519 to 522, 516 to 519. Okay, so that gives us our brackets there. We can then continue that. Okay. So that's what this incremental search is really about. If we then have these, we now have this array of brackets, and you can then loop through this now, cycle through this, and put in each of these brackets into your F0 command, and you'll come out with each of these roots. Okay, and so this is 1, 2, 3, 4, 5, 6, 7, 8, 9 roots, and there are 9 roots that we decided yesterday on this function. Okay, as we have it, as we defined it here. Okay, so the first thing that you're going to do for these practice problems, and the reason why this is starter code, is there are some instructions at the very bottom here. Okay, well, actually, what I want you to do is make sure that you understand the code. Okay, so walk through each of the parts of the pseudocode and comments and information that's here, and then from this, make sure that you understand the display, what we're displaying, how to manipulate this. We have the in-argin, which is a brand new command. It's a really helpful command, and we'll start introducing that series of commands. But then there's an assignment at the bottom, which is to mark the bounds of each identified bracket on the plot for visual inspection. Okay, so here's what you want to do. You want to plot the function, use a 2-point blue line. You want to mark each lower bound of the bracket with a filled green diamond, mark each upper bound with a filled red diamond, and then definitely plot a black line across the entire domain so you can identify the zero crossings. And then I think it's smart, when we're talking about a well-documented, well-formatted figure, to in your title or somewhere on the plot, and here I'm prescribing in the title, how many intervals are you using, and what is your domain? So that way we know it's from 3 to 6. I'm using, 100 intervals, for example. Okay. And I can post this of what mine looks like. And so this is what my code looks like, where we can now, you can see incremental search using 100 intervals from x is equal to 3 to 6, x is equal to 3 to x is 6. And then as we zoom in, it gives, here's my left side, there's my right side. So you can see that, or that we can verify really easily graphically that we've gotten all of the intervals. The one that's going to be interesting is this one here, where we've got a green and a red and then another red. And that's because the green and the red are on top of each other. Okay, in this particular interval search, okay, the upper edge of this interval was also the lower edge of the next interval that the root was contained in. All right. So does this make sense? Are you guys following along with this?
Upload
Okay.
your code just to, for example, if you want to work on it on the weekend, and probably you guys aren't going to be there to check your code. zeros so we can check what we're doing?
Yeah, I would post to the forum. Put your code up there and get some help on that. I'll check my email over the weekend and be glancing. So I think we'll all respond to the forum as well.
Okay, sounds good.
But the forum is the place to go. I know each of the TAs monitor it, and I monitor it myself. It's not being used, so our monitoring it's kind of for naught right now. But that being said, that's the place to go get that help.
Okay, sounds good.
Okay. All right. Well, good deal. All right. So what questions, what other questions do you have about this concept? Does the concept make sense with the interval search? You guys feel pretty comfortable with that? All right. And I want you to add some plotting to it, and I want you to use it. So that would be the first thing, is adding the plots to it. And then the second parts of the assignment, you'll see it posted on Canvas. You're going to be doing the same problems, the same practice problems that you used last time. Okay, and last time it was use the graphical method, mess around with the F0, which is good to do. But then now use your bracketing, okay, your interval search to come up with the brackets. And once you got the brackets, then use an F0. So follow it with an F0 command with each of those brackets to find those roots exactly. Okay, so moving away from that brute force graphical method. Okay. And next time we'll be using another algorithm, which is a bracketing method to actually get the root. Okay, this time we identified the brackets. The next time we'll actually take those brackets and zoom into what the root actually is. Okay. All right. Well, if there's no other questions or immediate questions, definitely. Oh, do we have fundamentals due this week? Should have checked on that. Okay. What is it? Carter's nodding his head. What does it go through this week?
I think it's 11 and 12.
11 and 12. Okay, so make sure that you've done 11 and 12, and that you send that link to your TA for full credit on that. All right. Well, y'all have a great weekend. Thank you for coming to class. Those handful of you that are here. It's really helpful for me to see you here, even though I can see your faces. But yeah, really appreciate it. And we'll see you on Monday, and we'll just continue. We're going to be doing roots for the next week. Okay, different ways to do roots. So just get used to finding zeros in a bunch of different ways. And we'll introduce a couple more MATLAB tools next week on how to display and manipulate these functions. All right. Y'all take care.
Thank you.
Thank you, Dr. Davidson.
See you guys. You're welcome.